All right, so let's start. You guys all know me, so I don't need to introduce myself. So instead, I'll introduce today's topic instead. I'm going to talk about trying to reduce the calculation time of knot invariance. So let's so before I talk about how I'm going to reduce it, let's talk about what we're trying to do. So the following is kind of paints a picture of how to calculate the Kaufman bracket. So basically, the idea is that for each of the crossings, we'll start by taking the first one, and with the first one, we'll apply the smoothing formula and split into basically two cases, and then we'll go to the second one, and we'll just keep going, keep smoothing out, and at the end, we add everything together and we obtain a Kaufman bracket. So with that, one thing we did notice is that every time we add a new crossing, for example, this one, we'll have to go back and check how it connects to the crossings that have already kind of been smoothed out. So every time we do that, we have to process this quote-unquote certain amount of information, right? So the question is, like, the more information that we'll need to process, the longer this Kaufman bracket or Slashow's polynomial calculation is going to be. So the idea is if we can reduce that amount of information we need to process, and what we're going to try and do is that if we just switch the order of the crossings around, then perhaps we're going to be able to at each stage need to process less information and help us reduce that calculation runtime. So now this term information at this point should sound a little bit confusing, so let's just rigorously define it. But before we need to talk about what this exactly rearranging crossing business is about. So given a knot K with n crossings, we're going to define a permutation of a knot to be a presentation of this knot such that the crossings are x of sigma k comma 1 to x of sigma k comma n are arranged in order from left to right and is equal to the crossings x1 and xn in some order. So in plain terms, what this means is that it is a presentation where we move the crossings around so that it is arranged from left to right. So with that, let's define this information that I'm talking about. So we will define the virtual width of at a crossing of given a knot permutation to be the number of segments connected to crossing, to crossing that is the crossing that we're looking at and the crossings before on one end, and then connect to one of the future, quote unquote, future crossings on the other end. What I mean is this. So let's look at this knot permutation, and let's look at the first crossing. So the virtual width will be represented by the line segments connected to the first crossing on one end, and then the second, third, or fourth crossing on the other end. So therefore, the virtual width here is going to be 4. And we go to let's look at the second crossing. Then the virtual width is going to be represented by the line segments connected to the first or second crossing on one end and the third or fourth crossing on the other end. And in this case, it is still coincident. Wait. Yeah, connected to the first or second crossing on one end. And it is going to be 4, although I did make an error I want to clarify here. Shoot. That's not what exactly I wanted to do. The line segments that truly represent the virtual width is actually the 2 blue ones here, this line segment, and not these 2. So the virtual width will still in this case be 4. I just want to clarify that before we move forward.
Yunchi, I have a question.
Go ahead. Yeah.
I'm not quite understanding. I think my question goes back to your definition of information as well. So or yeah, the previous slide. So you're saying we have a knot and we're given a bunch of crossings x1 through xn.
Yeah.
But a knot is more than just a bunch of crossings, right? Is there some sort of labeling for how they're connected, or is this like from the knot you just pull out like n pieces of information that's just the crossings, and so there could be many knots that have that many crossings, or like am I able to
Okay.
knot from the crossing?
Okay. I think I understand what you mean. So let's look at a to answer the question, let's look at a trivial knot. So it will look something like this. I really failed to explain this properly, but what I really meant is that, so the trivial knot, and let's first label the line segments that comes with it. So like the line, what I mean by line segments is that it's going to one and be on one of the crossings and one and be on the other. So let's just arbitrarily label it. I'm probably not labeling it in the conventional order, but for now we'll do that. And then what's going to happen is that a knot permutation will look something like, for example, I take the 3 crossings, I'm putting it on left to right, and then I'll say the first crossing in the permutation is going to be this one, for instance. So then I will look at what the line segments coming out of it is going to be. So it's going to be 2, 5, 6, 1. And then the second one is going to be 4, 6, 5, 2. And the last one is going to be, well, let's just say 4, 2, 1, 3. One sec. Let me just quickly look to see if I want to make any changes to that. Yeah. Okay. So with that, then we will connect the line segments into its rightful spot. So the endpoints together. Wait, hold up. I definitely did something wrong. So 2. So this is 2. And this one's going to be 3, 6, 5, 4. So then the connection is, for instance, going to look something like this. And there I created a permutation based on just putting the crossings in different order base and keeping kind of bookkeeping the line segments that is going to come out of it. Does that make sense?
So you're just taking the crossings and then flattening the picture so the crossings occur in like a line from left to right?
More flattening. I think flattening could be a right word, or like just basically moving them crossings around.
So you're choosing ordering of the crossings?
Yes. I can choose this one, or I can instead choose, like, I will select this one first and then this one and this one, or this. Like, I can do it in all kinds of orders as I please.
Okay. So yeah. When you're choosing a permutation of the knot, you're choosing an order of the crossings.
Yeah.
Okay. Yeah. Okay.
That's a good question. This definition the definition alone made sense in my head, but clearly I was missing something. So
then can you describe what the width is for this, or like can you
give me... yeah. Perfectly. So let's look at let's look at what the width at the second crossing is, because that I think will be more interesting. So we're going to look at the width is going to be represented by the number of line segments connected to these two crossings at one end, and then connected to the third crossing at the other end. So in other words, we're just kind of going to be looking at the line segments connected to the third crossing. 4, 2. So I just connected 4 line segments, so therefore the virtual width for this crossing is going to be 4. Does that make sense?
Can you say why you left out the 2 blue?
So because so the requirement of a line segment being representative of the width at that point is that it will have to connect to one of those 2 crossings at one end, and the other end it has to connect to a crossing here. So like beyond the second crossing. So the 2 blue lines that I left out, both of its ends are connected to a crossing in the kind of first set.
Okay, so you're using the ordering to determine which ones you have to go.
Yeah.
Okay, cool.
Yeah.
Okay. Thank you for doing that.
No problem. Okay. So with that, so now we've defined what a permutation is. We defined what the width is. So then we want to reduce this information piece. So there are kind of 2 ways we can go about it. Is that first we can find what I would define as a minimum virtual width permutation. Basically, it is basically going to be a permutation such that all other permutation have oh shoot, I need to mention this. With the virtual width that each crossing defined, I'm going to define the virtual width of the entire permutation to be the maximum of the virtual width at all crossings. So for example, in this case, the virtual width here is 4. The virtual width here, as I shown, is 4, and the virtual width after the final crossing is third crossing is going to be 4, and then the final crossing is going to be 0 because everything is going to be connected. Because there's nothing on the other side, no crossings on our side to be connected, so the overall virtual width of the permutation is going to be 4. So one thing we can do is that we can find a permutation such that all other permutation have virtual width no less than the virtual width of this permutation M of k that we found, and we will call the minimum virtual width permutation. And we do know that there could be many different minimum virtual width permutations. This does not necessarily have to be unique. And the second one is that we can also look at some constant corresponding to a runtime of calculating a particular knot invariant, and this constant is going to consist of the different virtual widths the virtual widths at all the crossings that we calculate, and we'll seek to minimize that. If this sounds confusing, I will come back to this later. For now, I will start with finding the minimum virtual width permutation. So to find out what the minimum virtual width knot permutation, we need to show how to kind of calculate the virtual width of a permutation. And to be more defined than what I'm saying is that I want to be able to do it computationally. So thankfully, this is not going to be hard to do. So we know the virtual width after the first crossing of any given permutation is going to be represented by the line segments coming out of the first crossing on one end, and then connected to any other crossing on the other end. In other words, it's going to be represented by the 4 line segments connected to the first crossing. And then to establish what the width after the second crossing is going to be, we can do this recursively. So we know the first, and then for the second, we're going to for the width after the second crossing, we can add the line segments connected to the second crossing on one end and connected to a future crossing, let's say third, fourth, fifth on the other end, and then subtract from it the line segments connected to the second crossing on one end and a previous crossing, in this case, just the first crossing on the other end. Then at that point, what we're going to obtain is the line segments that's going to represent what the virtual width after the second crossing is going to be. In this case, the virtual width after the second crossing is still going to be 4, and we can continue this process and figure out what the virtual width of a not permutation is, and from there we can find the minimum virtual width permutation for all knots from 3 to 10 crossings, or we can also say that we can find ourselves the order of the crossings that we have such that the virtual width of permutations involving those crossings in specific order is going to contain quote unquote the least information. So technically we can computationally do that and we can call it a day. But what is going to make this more interesting is that if we can draw out and visually see what those minimum virtual width permutation is going to be. But that is not going to be an easy task. So to illustrate that, we're going to, yeah.
All right. So I just want to make sure I'm understanding you right. So is the idea that like to do the Kaufman bracket, you have to just like pick a crossing, resolve it, and then you have these 2 new diagrams, and then you have to pick the next crossing and resolve it. So are you saying that to compute this faster, you're trying to like optimally choose which order of crossings to resolve, so that will yield
Yes.
the number of computations overall? So you're predetermining, just like doing this quick computation of width to predetermine that order. Is that
Yes.
it? Okay, cool.
Yeah. Okay. So with that, let's look at the following knot. The PD notation looks like this, and for visual, the knot diagram of this knot is going to look something like this. And we want to be able to draw out a diagram of what a minimum virtual width permutation presentation could look like. And that is, so upon examination, we determine that permutations where the crossings arranged from left to right is this order is a minimum virtual width permutation, and to provide clarity, the order of the crossings is going to look something like this. And what we want to do is that we want to be able to kind of connect the dots and connect the line segments together and somehow form a permutation. But turns out that is easier said than done. So what we're going to do first is that we're going to make things simple. If we look at the first and second crossings, because that is naturally a place to start, just look at the earliest crossings and connect. And we notice that we want to connect line segment 9 on the first crossing to the line segment 9 on the second crossing, basically completed. And we can do that along with, by the same logic, line segment 18, and the first 2 crossings as connected would look something like this. And then what we're going to try and do is that we want to somehow connect the rest without ever having to circle around other crossings. What I mean is, for example, if I want to complete segment 7, I want to do something like this, for instance, but not something like this, where the line segment end up circling around segments that circle around crossings that a segment is not connected to. For the rest of this talk, I'm going to refer to those as circling crossings. just as a definitional standpoint. So with that, we want to try and avoid it because every time we have to do that, the process becomes more complicated. Because for instance, if we do go down this route, then if we want to connect to one, we'll have to determine then how is one going to connect to help us build around the fact that we have just kind of enclosed this entire area, more or less. So we're going to connect 10 next because for no other reason than that I just see a straightforward connection going from the left to the right, and we're going to do that. And once that is established, then we notice that 17 and 18 are the first crossing. Well, we have to kind of go on top of everything to make sure we don't have this annoying circling crossing business that we're talking about. And at the same time, we're also going to connect. So we do the connections. I want to use a blue pen step because this is a good step, not a bad step. So I want to connect 17 next, and then 8. And this point, we realize 1 where we have this little hole we can connect out of. So we're going to do a connection. At this point, I do want to note that I want to go back to this and say I put the crossings intentionally in this order, such that the bottom right crossing is going to be the bottom line right line segment is going to be the same as the first of the 4 numbers I see in the PD notation. If we look at this diagram, we will realize that we can theoretically rotate this crossing 90 degrees clockwise without any harm. But for simplicity's sake, we'll ignore it for now because as I said, it doesn't hurt us. So then we can also connect 7. And at this point, we kind of have a problem because if I continue the same process with 16 and connect it like this, well, 2, 6, 11, 15 it's kind of trapped. We cannot connect it to the other end. Let's say 2, it's here. Then I cannot connect 2 without creating a virtual crossing. So that means that 16 has to be a circling crossing somehow, and that makes process more complicated. And also, I could have done this entire procedure differently. Notice at this step, I didn't really explain why I chose to connect 10 first before everything else. Because in fact, if I choose a different order, I can actually end up in a case where 1 and 10 are actually the circling crossings. Rest of them that you see having already connected are not circling crossings. And the more problematic part is that these 4 crossings are going to go to the quote-unquote right of the 5th crossing in a different stacking order if we had 1 and 10 being circling crossings as opposed to 16 being the circling crossing. So the moral of the story is that what we do at the previous steps is going to have a very, very much important effect on what we do on the later steps. And it's going to be difficult to gauge like what we should have done first and what we shouldn't have done first. So at this point, we want to see a motivation is that we want to see if we're able to kind of rearrange the order of these crossings. So maybe we can get rid of the problem that I said, like, I don't want circling crossings. I want everything. I can just go left to right and connect everything in a very much straightforward manner. And to add to the need of that is that I intentionally kind of ignored what the first crossing looks like. But the first crossing, in fact, can kind of go to the right to connect to other crossings in 4 different orders in terms of how the line segments stack on top of each other. So here the 1 denotes the crossing that is kind of the represent whose number is going to be the first in the PD notation of that crossing. And you can see there are 4 ways which the line segments can quote unquote leave the crossing. And this is this is obviously inevitable if it's a first crossing, but let's say if we rearrange order in such a manner that the fourth crossing end up needing this procedure, well, then we kind of have a problem because now all of a sudden we have to multiply the possibilities that we need to account for by 4. That makes it computationally really difficult to define. So we need to work around this. So as you can see, as I alluded to, I want to connect everything straight. And to do that, we kind of need a system to bookmark. For example, if I draw a line here, right? If I draw a line here, I want to know what the how the line segments stack on top of each other going through this line, so I can determine how I use the points on this line to connect to the rest of the crossings. So with that, I'm going to define what is called a graphical width. So graphical width is not a complicated one to define. It is basically if I have a knot permutation as, for example, the one that I drew early in this process, I will just draw a line. I will not draw it now because this diagram is already a little bit messy as it is. But I draw a line and see how many line segments does it cross, and I will just denote that to be the graphical width of that permutation. So now we have a bookmarking system, but the problem is this bookmarking system is kind of complicated until we see what the knot diagram actually looks like, which kind of isn't in line with what we're trying to do, because we're trying to create what a knot diagram looks like, but then this process requires to even use this, we need to create a knot diagram first, which it doesn't make any sense. So what we're going to do is that we're going to define something similar, but it's going to be computationally easy to bookkeep. So, but to do that, we want to know what is the task at hand when we connect it to the next crossing and what we already have. So with that, we're going to define something called the left and right fronts. So left and right fronts are in essence denote the information of what we need to take care of every time we bring a new crossing in. We're going to define the left half front of at a crossing to be aligned directly to the left of it, and then the points on it is going to be the intersection points of the line segments coming out directly out of that crossing. So in this case, we notice in this crossing, 2 of the line segments go to the left, 2 goes to the right. So therefore, the left half front is going to have 2 points. We can define the right half front in a similar manner, and it will have 2 points on it as well. So with that, we can officially really simplify what our graphical width is going to look like. So we will define a permutation. There should be a comma here. Permutation to be a quick width permutation if the following are true. Before I read out a definition, in essence, it will get rid of all the problems that I was mentioning. So first, I want to have only the first and last crossing to have empty left fronts and left half fronts and empty right half fronts respectively. So what this means is that, for example, I'm not going to have the fourth crossing looking something like this. This fourth crossing of, let's say, a 6th crossing knot looking something like this. This is not allowed, and so isn't this. The second thing that we want is that we want no line segment to intersect the front twice, because that is a problem when we were looking at something like graphical width here. Because if we have a line segment intersecting a front twice, we need to be aware of how these line segments relate to each other, and that makes it difficult to bookkeep. And the third point is that we want to connect the points on each front to half fronts immediate to the left and right without creating virtual crossing. So what this means is that, for example, after a certain amount of crossings, I know what line segments remains unconnected to. Then I go to the next crossing, and let's say I've left half runs, and we're trying to connect the line segments together. I want to be able to connect the line segments like this without needing to creating virtual crossings, which will bring us a need for a subsequent crossing, which is annoying. Now we have this established. We can see that drawing a knot diagram becomes a lot easier because we can just now more or less connect from left to right. But what I didn't say is, if let's say I have a knot, if quick width permutations actually exist for it.
Yunxi, I have a quick.
Yes.
So, are you describing a braid here? Does a quick width permutation have to be a braid? Because this idea that you're not allowing to like come back and then go forward or come back, like it's kind of a monotonically going one way. Are you just like proving Alexander's theorem or recovering Alexander's theorem? If you don't know the answer, that's okay. But that's just what came to my head.
I don't have an answer to that question. But yes, it will make sense that it will definitely look at some sort of braid structure. Like if we go back here, on top of my head, is that like theoretically it does look like to me when we cut off the beginning and it sort of looks like a braid. Professor, am I saying this right, or am I saying nonsense right now?
I think it's not quite the like the usual closure of a braid, because you have but it's kind of like a different closure of a braid, like because you're allowing to like cap off this direction. Anyway, don't let me stop you, but just braids are there somewhere.
All right. So with that, where am I? So going back to a question, does quick width permutation exist for all knots? Well, we kind of have to check. So how do we check it? Well, we're going to be going through the permutation, all the kind of crossing permutations, and from there we're going to try and use that to establish quick width permutations. And if we can establish it with any crossing permutation of crossings that we start off with, well, we have created quick width permutations. If none of the permutation of crossings would help us produce quick width permutations, then, well, that knot doesn't have quick width permutations. So this is how we're going to do it. So I'm going to go through how, given a permutation of crossings, we develop potential quick width permutations, and we'll have to kind of check it through for all permutation of crossings, which I will obviously, for time reasons, not do. So let's look at this permutation of the crossings. This was taken off the trivial knot, and in likely a different line segment labeling order. First, we're going to go ahead and establish the left and right half runs for all crossings except the first and the last, because as I alluded to earlier, this is a little bit more annoying to set up with 4 possibilities. So what we're going to do is that, because we kind of want the line segments to go straight to the left or straight to the right based on what on the other end this line segment is connected to, we can go ahead and say, look at, for example, the second crossing and say, if the line segment connects to a crossing to the left of the segment in question, we're going to extend it to the left half run, and then opposite way, we're going to extend it to a right half run. This is kind of a bad example. We can feel, because the line segments are already kind of in that position, but theoretically we can also have something like those three going to the left and this going to the right half front instead. So then the left and right half front would look something like this. So the left half front has 3 intersection points on it, and the right half front is 1. So next we're going to tackle the first first annoying thing is that we're going to go ahead and establish the first right half front in terms of what it looks like. So basically we're going to take care of all 4 of the order in which the line segments can stack on each other when we try and connect the line segment to crossings on the right. So there's 4 ways we can do it. So then at this point, what we're going to try and accomplish is that we have this, and we have this second left half front. So what I'm going to do is I'm going to try and connect the dots with the points that are both on the first right half front and the second left half front. And it will ultimately look something like this, right? So 4, 1, 4, 1 is going to be connected, 4 and 4 and etc. If at this point I created a virtual crossing, for example, in this case, I'm going to reject this case as being impossible. What I'm rejecting right now is that I'm rejecting the order of which the line segments leave the first crossing. Now, if at this stage I reject all of the possible orders, then I have rejected a crossing permutation as being impossible to produce a quick width permutation. But otherwise, if I don't reject all of it, I will take the remaining ones that are unrejected. I am just going to extend everything to the second right half front. Theoretically, if we have more crossings, then we can repeat this connect the dots, extend and reject process over and over again. But if we arrive at, but in this case, I obviously can't do that because we have arrived at the last crossing. At last crossing, what we're going to do is that we're going to just connect it by any means possible, because at this point, we don't have to take care of the circling line segments problem, because if we need to circle beyond the however many crossings we have, we can just theoretically quote unquote circle it around the last crossing, which wouldn't really be circling, because at the end of the day, the line segment is connected to the last crossing. So what we're going to do is that we do that, and if we still need to produce virtual crossings, we reject the case. Otherwise, we have produced quick width permutations. And note, I hope I made this clear at the beginning, but if I didn't, permutation is simply what a presentation of a knot looks like in terms of knot diagram form. It doesn't mean that given a permutation of the knot, I can only produce one permutation. In this case, I have one permutation of the crossings. I produce 3 different permutations of the knot, and that's perfectly fine. But either way, we have produced quick width permutations. So at this point, we can repeat the process for all crossings with size between 3 and 10 inclusive, and conclude that all of them actually has a quick width permutation. Now, if with those extra conditions that is needed for us to, quick width permutation, and I want to take a step back. I want to define the minimum quick width of a knot to be the minimum virtual width of all the quick width permutations. So what this means is that, for example, in this case, the minimum virtual width we know is 4. And we're going to take all the possible quick width permutations and look at what their virtual width is, and then pick these, and we got ourselves the minimum quick width of the knot. And now it will be useful for us to compare what the minimum quick width and the minimum virtual width of the knots are, because we did impose some decently strict restrictions in what a quick width permutation is. So We want to figure that out. And also we want to know how this relates to the graphical width, because at the end of the day, we are drawing knots diagrams and we want to know what it looks like. So at this point, we can computationally determine that for most of the knots, the minimum quick width, forget something here. Is going to be equal to the minimum virtual width. But there's 6 exceptions in that those out of the, I believe, 250 knots where the minimum quick width is going to be greater than the minimum virtual width. Specifically, none of these are in in such that the crossings are arranged from left to right. This is just an illustration of what the knot looks like. In those 6 cases, the minimum quick width is going to be 6 and the minimum virtual width is going to be 4. So we know the relationship between quick width and virtual width. Now we want to know what the minimum quick width kind of permutation, so the knot diagram we draw are going to look like. So we're going to try and relate it back to the minimum graphical width. So how does that relate? Well, we know that in a quick width permutation, the virtual width of the permutation is going to be equal to the graphical width. This is because in a minimum quick width, we're able to bookkeep the what the graphical width is in a manner where we don't have to account for circling crossings or anything annoying of that nature. So we know that the minimum graphical width in these cases are going to be at most the minimum quick width, which is going to be 6. We also know that the minimum graphical width is at least the minimum virtual width by how we define the virtual width. So we know that the minimum graphical width is going to be at least 4. So now it comes down to a case of choosing 4 and 6. And in fact, I'm going to claim that the minimum graphical width of these 6 knots is going to be 6, which is interesting in that what the width is kind of as from a computational standpoint is not going to be equal to what the width is from a graphical standpoint. So I'm going to very, very much quickly go through a proof. What in essence is that if we have a permutation of any of those knots where the minimum graphical width is 6, we know it's not going to be connected in such a manner where I can connect everything from left to right as a quick width permutation. Otherwise, the minimum quick width permutation is 4. So then at this point, we check through the rules and we realize I want to go back to the definition of the quick width to explain this properly. We can just ignore this for now because at the end of the day, the graphical width is based on knot diagrams, not virtual diagrams. So then it comes down to which one of those 2 rules does this knot permutation of graphical width 4 violates. Where it actually cannot violate this condition. The reason being that if this condition is violated, let's say I have something like this, then because the entire knot or the entire diagram is connected, I would actually need extra line segments to go to the right and go back to the left of the crossing. So the graphical width in this case have to be 6. So therefore, we're down to the scenario if the graphical width is 4, that's such that we have line segments intersecting in front twice. But the problem is that in essence, if we have some annoying like line segment that intersects the front twice, we can just pull let's say the leftmost or rightmost point depending on how the line segment runs. We can just pull it to the right of the front because there cannot contain a crossing in this area formed by the line segment and the front. So then we repeat And we end up seeing that if the minimum graphical width is 4, then the minimum quick width will be 4 because we'll be able to use this pouring technique to create a kind of quick width permutation of it. So therefore, because of this restriction, we find that in all 6 of those cases, the minimum virtual width, so what we use in computing knot invariance, is not going to be equal to what the graphical width is going to look like from a knot diagram standpoint. But regardless, and with that information, we can theoretically create presentations of what the minimum quick width permutations of knots look like. And for example, this one is a minimum quick width permutation of knot 913, so which is the knot that we were looking at. But we do also have to watch out for those 6 exceptions, because here we have created a permutation of a minimum virtual width knot, minimum virtual width permutation. So like what we can actually use to calculate knot invariance in almost the most efficient way possible. But in those 6 cases, we'll have to say we can't do that. So going back to the beginning of the 2 tasks that we're doing, I have more or less explained what the minimum virtual width permutation is going to look like. So now I'm going to get to the part where I'm going to try and explain what this constant is. The motivation of such constants appearing is that when we get to bigger knots, because ultimately, like when we calculate knot invariance, we're usually looking at bigger knots of which we want to calculate the knot invariance from. And we cannot really cannot repeat this process of trying to find the minimum virtual width by looking at every single crossing permutation. So we want to be able to somehow minimize the runtime in some way. So what is this constant that I'm talking about? Well, we know that algorithms have runtimes that can be summarized by the big O notation. For example, the most efficient sorting algorithm that we know right now, its runtime can be denoted as O of n log n, where the n is the number of items we want to sort. So then going back to the confluent bracket calculation algorithm, the question is, can we come up with something similar? Well, it turns out we can. I'm going to claim that the runtime is this, where n is obviously a number of crossings. So to very quickly explain what this whole thing is about. So at each step, we know that there's, let's say, 5, 6. For example, if the virtual width is 6, as kind of how we're going to, how many things, let's say, if we add in a crossing that the strand is going to connect to, then we'll have to check. So given the width, we want to first estimate or know how many possibilities could the crossings we've kind of already smoothed out can be connected. So like, for example, I could have connected this. This is just a tremendously bad example. So for example, the crossings below could have looked smoothed out into something like this. I'm just drawing something like this. It might not be entirely accurate, but the idea is that the number of ways we could have smoothed the things out correspond to the number of ways we can connect line segments below the crossing to the kind of the unconnected strands that we're going to connect future crossings to. And that number corresponds to the kind of number of the width divided by 2. And then, as I alluded to, for each of those possibilities, we need to check first of all, we need to check through the width to see if this new crossing is going to connect to, let's say, any of the line segments that's going to be represented by the width. So that is where the width comes from. And finally, the K is just simply the number of crossings that we have smoothed out beforehand that could have produced terms that we would need to check for, that would need to check if, quote unquote, a connection occurred computationally. So this is what a runtime of calculating confidence bracket looks like. So the question, so if we're able to use something like this to estimate the runtime, then we'll be able to develop algorithms that could potentially tell us, let's say we rearrange the order of those crossings, if we have truly reduced the runtime of trying to calculate constants such as confidence bracket. For example, if let's say the width of a particular permutation is like 4, 6, 6, 6, 4, and 0, because the virtual width at the last crossing is going to be 0. Intuitively, we can probably confidently say, wait, no, I want to change the third one to a 4. If we are able to reduce the width to something like 4, 6, 6, 4, 4, 0, then I think we could, wait, hold on. 4, 6, 6. This is not what I wanted to say. Originally 4, 6, 4, 6, 4, and then now the widths are this. So then we can very much confidently say that the resulting runtime of trying to calculate the confidence bracket of this is probably reduced, because the only thing we have done is to reduce the information at a particular point. But what this formula is going to, where this formula is going to be particularly useful is going to tell us, for example, if we instead come up with something like four, where the width is going to be 4, 4, 4, no, 4, 4, 6, 4, 4, 0, right? If we came up with something like this, we can use, hopefully we can use maybe this formula to help us determine if this, for instance, is better than the first one or even better than the second one. So this is where the constant is important. And we're going to denote this constant by S for the rest of this talk. Intuitively, we want to say if we can write the estimated runtime, which will denote capital T, as some constant little t times S. If we're able to do that, then it's sufficient to just calculate this, which is often very much more efficient because the only thing we'll need to do is to calculate the virtual width at each crossing.
Yunchi, quick question.
Yes.
So in the example that you have just above, if you could scroll up there. So yeah. I'm trying to understand the difference between the bottom two lines. So you seem to have moved the 6 to the right.
Yes.
So is the idea that that should be better because then the CW sigma K term is going to be smaller or something like, so you want to like front load your computation with smaller numbers first, like put the larger numbers last or something? Is that the idea? Or? Well,
you kind of spoiled it. The only thing I was going to mention that later, but the only thing I was trying to allude to here is that the constants can help us see which one of those is better. But yes, the results end up being that we should front load it.
Okay. Yeah. With smaller numbers first.
No, it actually, given a choice, we'll have to front load it with bigger numbers first. So this is because like the 6 here, when we multiply this K constant, this 6 is going to actually have a much larger effect here than at here.
Oh, I see. Okay.
Yeah. But I will also elaborate on that later. I noticed that we're running out of time. Shoot. Okay, so very quickly, it turns out we're able to actually use this formula in that the runtime is somewhat correlated to the S value. So what I've done here is that I took 70 different knots in a giant list of knots provided by Dunfield. And by the greedy algorithm, selected a permutation where the runtime of calculating Kaufman bracket is going to be decently small. I also collected a S value for it, and then take the ratio of T divided by S. And as you can see, surprisingly, that the numbers all hover somewhere around like 0.00015. So I'm going to write it because it is kind of small. So 1.5 times 10 to the negative 5. And then the lower bound seems to be bounded by like 1 times 10 to the negative 5. So with that, we can kind of say that the T divided by S value is going to be equal, can be estimated by some sort of constant, which in this case we'll call this to be the constant because it seems like the T value seems to be hovering, sorry, the ratio value seems to be hovering around this number. So with that, I'm going to very quickly go through what I've done to take advantage of this. So the idea is that I can't go through all the permutations of the crossings, but what I can do is that I can select small chunks of crossings and then see what the permutation of those crossings should be in terms of trying to minimize this S value and ultimately reduce the runtime. So the first idea is that I take the first 5 crossings, I scramble them and see which order they will be best in trying to reduce that S value. And then I would leave what I found as to being in need to be the first crossing behind, and then I will do the next 5, and then I will just keep going and keep going. And in fact, what we see is that it's actually going to help reduce the runtime of calculating Kaufman bracket. So we will denote the size of the chunks to be X, and what we notice is that, ignore this part of the diagram, but I generated 10 different greedy generated permutations, and then I conduct this local optimization technique of trying to optimize it one chunk at a time. And I notice as the resulting S value will definitely decrease as I kind of increase the X value, especially like as at X equals 5 and at X equals 6, the decrease will become much more significant. And also, however, one thing that we can notice is that there is sort of this inconsistency in both what we get out of the greedy algorithm, because we did set, for example, if we have ties at each step of the greedy algorithm in which we select the next crossing, we're going to randomly select it. So this randomness brought inconsistency, and also the local minimization is not guaranteed to be good. For example, in this purple one, the local minimization did reduce the S value by a lot, but this green one, not so much. So one thing that we can do to improve it, and this is one thing that I learned that people do all the time before they actually go in there and calculate the knot variance, is that we'll take 1,000 of those greedy algorithm generated permutations and select the best one and just work with that one. So with that, just work with that. However, as Nancy did lead me to spoil a couple minutes ago, we did notice in this formula that the later the bigger number is, it's going to get worse. For example, if let's say the number of crossings had increased to actually 100, which increased to 100, then we rather this 6 be earlier, let's say at the second or third width, than to be later at like the 95th, 96th width. because at that point, this extra k constant we apply is going to increase the S value by quite a bit. So with that, we could choose instead to reverse this process so we're going to start from the back. So the back, let's say X crossings, and move to the front. The reason that we're doing this is that we want to shuffle, sorry. Oh yeah, right here. We want to shuffle everything. We want to shuffle the bad things to the front as fast as I possibly can. And with that, we kind of reverse the local minimization process I was mentioning. And we can see we're going to be able to get a better results. So for now, we're going to focus on the local minimization and the reverse local minimization. This is what the 10 samples is and what the S value is going to end up being. If I apply this with the chunk size being 6, I selected 6 out of arbitrary. I would love to be able to explain why I selected parameters, but we'll see on time. But we do notice that for the reverse case, in a lot of cases, the S value did decrease further. Although it also depends because in some cases it did get worse. Now, the problem with either one of those algorithms is that it takes a long time for me to shuffle everything around. And for example, if I just, going back to the local minimization, if I just shuffle it once, then for example, this 7th crossing in question, so it is, I cannot get to it until I get to the 3rd kind of chunk of crossings that we're trying to minimize. So the earliest I can shuffle this crossing is to the 3rd. But this begs the question of what if in reality the kind of best permutation is if this crossing indeed should have gone to the 2nd. And this problem is also similar for the reverse local minimization, where I don't have enough time to shuffle. And when I say I don't have time, I literally do not have time, because each of those, like taking these chunks and shuffling from left to right, this process takes time because I have to check through every permutation, and it gets worse as the size of the chunk increase. So oftentimes I'm only able to shuffle it once. For example, in this following example, I took quite a few, I believe it's 10 of greedy samples via selecting the best out of 1,000 greedy algorithm generated permutations. And then I try and estimate the time it will take to calculate the Kaufman bracket based on the formula here. And then I also conduct linear optimization, so this shuffling process once, and then 0 times, 1 times, 3 times, and then we will need to add the number it takes add the time it takes to shuffle to the estimated amount of time it would take to calculate the Kaufman bracket. And we'll see if we shuffle it once, we will probably be able to reduce the overall time we need to spend. But if I shuffle it 3 times, then the time actually increases to a point where it becomes kind of a moot point to even consider shuffling it 3 times. So to solve that problem, I want to be able to shuffle many times while putting the dots in place. And one idea is that I could potentially, every time I shuffle, I want to get a good enough shuffling result instead of the best one. Because at the end of the day, if it was really bad, then I can theoretically shuffle it to get it to be good enough. And at that point, I will be able to minimize the runtime already. Then the advantage is if I get it good enough every time, while spending way less time shuffling this, I could potentially shuffle it many, many times and move the crossings to a more optimal spot. So what I'm going to do is that what I'm going to do is that instead of running through, let's say I'm given a chunk of crossings, instead of running through all the permutations with those crossings, I'm going to take 10% of those permutations plus what the original permutation of the crossings is. And at that point, I'll be able to hopefully be able to do a decent enough shuffle while spending way less time on it. So I'll be able to shuffle it again and again. The reason I'm going to be able to shuffle it again and again, because now I'm only checking 10% of the permutations, which basically takes 1/10 of the time. So when we do that process, we can notice that the resulting S value is going to be lower than if we had conducted local minimization. So the original reshuffling process, which is kind of what we were expecting. And then we can apply the same logic we did to local minimization, and we say instead of doing the shuffling every time from left to right, we're going to shuffle from right to left, so like the back to the front, to be able to reduce that over S time even faster, because now not only we're doing the shuffling faster while still getting diesel results and being able to repeat, I'm able to also focus on trying to bring the work, like the biggest virtual width, to the front instead of letting it stay at the back. And this time we're looking and going back to how the results will show up for once we conduct the shuffling process. We'll see that when we conduct the partial shuffle and the reverse partial shuffle, the resulting S value will be even smaller. And when we run it against a bigger samples that come from selecting the best of 1,000 greedy algorithm generated samples, the results become even more apparent in that I'm able to reduce the time it takes to calculate the Kaufman bracket, even if we also add the amount of time it takes to shuffle and local optimize everything, which I think will be needed. And we're able to see what, at the end, if we do the kind of the faster version of the partial shuffle, trying to come up with a good enough order of the crossings every time, and then we do it in reverse, we're able to come up with permutations of the permutations that will help us reduce that calculation time of the Kaufman bracket from originally it would take about 24 seconds on a size 100 knot to now we're able to reduce it to less than 20 seconds. And this will become even more apparent if, let's say, I start with a 200 crossing knot, which originally the estimated time it would take to calculate the Kaufman bracket is about 200 seconds or so. Now by just shuffling this, I'm able to reduce that Kaufman bracket calculation time by about a half. And we'll be able to see similar results if we just straight up if we just calculate the Kaufman bracket as opposed to calculate the Kaufman bracket and record the time as opposed to estimating the time it will take to calculate it. So I realize I'm running behind, but I have one last thing, is that when we compare the two sets of results, we did notice that in the 100 crossing case, having the chunk size of what we're trying to locally minimize every time be 5. Here it's going to be better than having the chunk size be 6. But in the 200 crossing case, it's going to be better if I take the size of a chunk to be 6 as opposed to 5. The reason this is true is because the process it will take to explain what this is happening, I will have to go back to explaining the runtime, right? Overall, our algorithm is going to be quadratic because generating greedy generating samples by the greedy algorithm, that is going to be a quadratic process because at each step, I will be looking at the remaining unused crossings and trying to figure out which one I should put in. And then the entire shuffling process I'm applying, if we fix the size of the chunk that we're trying to locally minimize, kind of locally optimize every time, that process is going to be linear because we're simply going from left to right. And the number of times we have to do that is proportional to the size of the knot. So because of that, it is very much reasonable to assume, and we are actually able to confirm, if the larger the knot gets, the larger the size of the chunk should be that we're trying to use to kind of optimally determine what order they should be, should depend on the size of the knot. So for example, I went back to Dunfield's list of knots, which has a lot of knots, and I took the first, I took every fifth of them for, I think, up to knots with 200 crossings. So what it means is that the width of the knots are going to be 7, 12, 17, and I add by each time. The overall idea is that in each selection, the knot size is going to get larger. And I went through the process of trying to estimating the actual time is going to calculate the coffin bracket added to the time to conduct this local, the conductor time is going to take to apply the the local minimization / shuffling process that we found to be the most optimal. And we realized for smaller knots, what I mean by smaller is like knots size up to like 100, having the chunk size equals 5 is going to be most optimal. And as we go beyond that, the size is going to start to turn into about 6. And as we get even further than that, this is
you're way over time, so you got to wrap it up. Just wrap it up real quick.
Give me 1 minute and I'm done. Yep. So I will take the 40 more knots with an even larger size. And what we notice is that as the size of the knot approaches, I believe it's like 300, having a chunk size equals 7 is going to be even better. So the moral of the story is this is going to be an algorithm that will be able to apply to larger knots with an even greater effect as the size of the knot gets larger. And that is what I have today.